Hello there and welcome back to the Shots in the Quark Special Relativity course. In this video, we're just going to be going over the basics of matrices. Matrices are mathematical objects that are very useful for representing coordinate transformations. And if you watched the last video, you'll have seen that coordinate transformations are going to play a major part in special relativity. So it's a good idea that we have their mathematics sorted before we move on to the physics. So we want to be familiar with the mathematics of matrices because coordinate transformations can be conveniently represented using matrices. So what is a matrix? Well, a matrix is a table of numbers or objects with a certain number of rows, n, and a certain number of columns, m. For example, we can write down a 3 by 2 matrix, which is a matrix with 3 rows and 2 columns, like this: 2, 6, 1, a half, 0, 3. Now you've probably already encountered a kind of matrix before because both row and column vectors are kinds of matrix. For example, a 1 by 4 matrix is a row vector, 1 row, 4 columns, 5, 4, 1, 3. And a 4 by 1 matrix is a column vector. It has 4 rows and 1 column, 5, 4, 1, 3. Okay, great. So what can we actually do with matrices? The simplest operation we can perform on matrices is to add them. Matrix addition is nice and straightforward, but there's one thing that you've got to keep in mind. In order to add two matrices together, both matrices must have the same structure, n times m. That is, both matrices must have the same number of rows, n, and they must each have the same number of columns, m. Assuming both matrices have the same structure, it's very easy to add the two matrices together. You simply add the corresponding elements in each matrix. For example, let's say that I have a 2 by 2 matrix, 1, 0, 3, 2, and another 2 by 2 matrix, 3, 4, 9, minus 1, and I want to add them together. Since they're both 2 by 2 matrices, I can add them together, and to work out the result, I just add the corresponding elements in each matrix. So I get 1 plus 3, which is 4, 0 plus 4, which is 4, 3 plus 9, which is 12, and 2 plus minus 1, which is 1. So that's matrix addition. Matrix subtraction is just the same as above, but you subtract the corresponding elements in each matrix instead of adding them. Now we move on to the most important matrix operation, which is matrix multiplication. And it's this operation which is the reason why matrices are so good at representing coordinate transformations. If you haven't seen it before, matrix multiplication will seem a little weird at first, but you'll get used to it after a few examples. First of all, like we saw with addition, you can only multiply two matrices if they have a certain structure. The two matrices don't necessarily have to have the same structure anymore, but you can only multiply two matrices together if the first has a structure n times m, and the second has a structure m times p. In other words, the number of columns in the first matrix you're multiplying with must be equal to the number of rows in the second matrix you're multiplying. Apart from that requirement, the number of rows in the first matrix, n, doesn't matter, and the number of columns in the second matrix, p, also doesn't matter. From this point, you might have noticed that the ordering of the matrices that you're multiplying actually matters. In mathematical language, we say that matrix multiplication is not commutative. In other words, if you have two matrices A and B, A times B will not in general be equal to B times A. The ordering matters. Now, to get familiar with matrix multiplication, let's see an example of it in action. Let's take a 2 by 2 matrix A, which is 1, 2, 0, 3, and a 2 by 2 matrix B, 5, 0, 1, 3. If we want to work out the quantity A times B, we write the matrix A first, and then the matrix B second. Now this is where it's going to get a little complicated. To work out what goes in the first row, first column of the result, we need to go into the first row of A and multiply it with the first column of B. So we have a 1 times 5, and then we add a 2 times 1. Moving on, to work out what goes in the first row, second column of the result, we take the first row again of A and multiply it now with the second column of B. Multiplying these two together, we're going to have a 1 times 0, and then we add a 2 times 3. Hopefully you're getting the picture now, but we'll go through the last two elements. To work out what goes in the second row first column of the result, we take the second row of A and multiply it with the first column of B. So we get a 0 times 5, and then we add a 1 times 3. Finally then, what goes in the second row second column of the result will be the second row of A multiplied with the second column of B. So we get a 0 times 0, and then we add a 3 times 3. The final result then is 7, 6, 3, 9. Also notice that if you were to work out B times A in this case, you would end up with something different. 5, 10, 1, 11. So this makes it very clear that B times A with matrices is not always going to be the same as A times B. It's at this point that we can see why matrices are going to be good for representing coordinate transformations. We can write the Galilean transformations that we saw before in matrix form like this. You can see that if you were to multiply these two matrices together, you'd end up with the Galilean transformations that we saw earlier. T equals T prime, X is equal to X prime plus VT prime, Y is equal to Y prime, and Z is equal to Z prime. It's much more useful to write down coordinate transformations in terms of matrices like this than as equations like we saw before. This is because it makes it very clear what the coordinates are and what the transformation is. The two column vectors represent the coordinates in the frames S and S prime. The big green matrix in the middle actually represents the transformation, and so we call it a Galilean matrix. Later on, when we start doing special relativity, we'll be using coordinate transformations all the time. Writing them down in terms of matrices makes it much easier to work with them. In order to transform coordinates from one frame to another, you take the coordinates in that frame and simply multiply by the transformation matrix. Before we conclude this section, there's just a few more things to mention. First is the identity matrix. The identity matrix is a matrix that has 1s along its leading diagonal and 0s everywhere else. So for example, the 4x4 identity matrix looks like this. The main property of the identity matrix that we're interested in is that in multiplication, it basically behaves like 1. If you have any matrix A times the identity, you just get that matrix A back as the result. The identity matrix is useful as it's going to allow us to define what we mean by an inverse matrix. The inverse of a matrix A, if it indeed has an inverse, not all matrices have one, is written A to the power of -1. What defines the inverse matrix is that if you take the original matrix and multiply it by the inverse, the result is just the identity matrix. It's like multiplying integers with their reciprocals. 2 times a half will be 1. Inverse matrices can be quite useful in special relativity because they represent undoing a coordinate transformation. If you've transformed coordinates from one frame to another and you want to get back to the original frame, then you multiply by the inverse coordinate transformation matrix. Finally, we just need to define what we mean by a transverse matrix. The transverse of a matrix A is written AT. What this operation does is it simply swaps the rows and columns of the matrix. So for example, if I have the matrix 1, 2, 3, 4, and I take the transverse of it, I'll get 1, 3, 2, 4. That's all we really need to know about matrices to start doing special relativity, and in fact, that's the end of this preliminary section. We've now covered all the basics that we need, and so starting from next video, we'll be looking at special relativity proper. Thank you very much for watching, and I hope you found this useful. See you on the next video.